Okay, good afternoon. I want to, on behalf of the Kavli Nanoscience Institute, I want to welcome you all to this special symposium, Kavli Future Symposium on Condensed Matter Physics. This symposium is made possible by the generous support of the Kavli Foundation and also the Jet Propulsion Lab. I hope you will enjoy the program today. The theme of this symposium, I'm going to borrow a few minutes from Duncan, just a couple of minutes. The theme of this symposium is on the physics and technology of the emerging states, emerging edge states from the surfaces and interfaces of novel materials and nanometamaterials. As you know, in the past decade, there have been lots of exciting developments in condensed matter physics. In particular, the advances in topological materials and in low-dimensional van der Waals materials have really stimulated directions for exploring new quantum states of matter and also for potential new technology. Also, the advances of nanotechnology have also enabled many possibilities to design new material properties on demand. And so concurrently, also, with Moore's law rapidly approaching its quantum limit, there is immense urgency that for us to develop new frontiers in materials that are capable of nanoscale functionalities. And so therefore, it is an exciting time, I believe, for top scientists and top engineers to get together to explore emerging physics and technology from novel materials. So without further ado, let's just, we can begin the program. Let's begin the program today. And it's my great pleasure and honor to introduce our first speaker, Professor Duncan Haldane. He is, among this audience, he is basically a person that does not really need much introduction. He has been a guru in theoretical condensed matter physics, and also he was Mr. Physics 2016, or what I meant was that he won the Nobel Prize in Physics in 2016.
It's kind of like Miss America, you
That's
know.
right,
The new crowd for your lot have taken over, so I have to weep a little bit.
Right. He had to give up his crown to Clifford, etc. Last year. Yeah. So anyway, he is going to talk about this fractional quantum Hall effect in flat lens. Basically a new goal to strive for topological physics. Let's welcome Professor Haldane.
Thank you. Okay, what I'm actually going to, I'm not going to tell you how to make a fractional quantum Hall effect in flat bands, because we don't know yet how to do it except in toy models. But I think because of the other two talks, we're going to hear about these new developments in the integer quantum anomalous Hall effect and putting superconductors on top of them, and it has a lot of great possibilities, which I think will be magnified tremendously if we manage to solve the material physics problem of making the fractional quantum anomalous Hall effect, which has the additional feature in it that you need to do some tuning to get flat bands to simulate Landau levels. But in fact, just the other day, there was Pablo Herrera was giving a talk at Princeton, and they managed to make flat bands with these Murray effects between boron nitride and graphene. So, you know, when there's a will, there's a way for these things, I believe. I've been very optimistic about how good our material sciences are, because they eventually, now we can take toy models, and lots of toy models actually get turned into reality now. We're still waiting for some of the beautiful non-abelian statistic things to show up, but given that we know such things can exist, somehow, somewhere they will be made into reality. Okay. So, like I say, so we really need to understand how we could design these kind of interesting materials, such as flat band stuff that shows not just regular Laughlin type quantum Hall effect, but of course we want to get the remarkable possible non-abelian thing. So to turn these from like toy models into reality, we need to know something about the energetics of what would possibly make these things actually happen and be chosen, as opposed to a boring abelian quantum Hall state. So we somehow missing a basic understanding of the energetics of topological material formation. Okay, so this is the well-known stuff, which I probably shouldn't go through. The zero field quantum Hall effect took a long time. I predicted in 1988 as a toy model, which I never really thought would end up as in reality. Now, it took some time, but the toy models are tremendously useful, I think, because they allow you to see all the kind of details about how things work. If you just have a general, very deep mathematical principle around it, it's difficult to see what it actually does without a concrete example. And the toy models turn out to have been great for all this topological physics. And there's all these things we see. We can see how it works. And in fact, as I say, the latest work, which we're going to hear about, was Chiku Shui's initial way to produce the quantum anomalous Hall effect by putting ferromagnetism on top of a topological insulator surface. And so the basic principle is you're using ferromagnetism to break the time reversal invariance rather than magnetic fields, so you don't have something that hates superconductors. And so the integer Chern insulator, the fractional, the quantum anomalous Hall effect, in some ways I think is, to some extent, the most possibly useful of the topological insulators so far, because it's got this rigorous splitting of one-way transport. With the time reversal invariant cases, it's much more delicate. You've got this two-way traffic, and provided the barrier in the middle of the road is high enough, they don't mix. But in the Chern insulator, you've got this fundamental distinction, spatial splitting of the modes. And of course, why superconductivity is interesting in this system is because we talk about symmetry-protected topological states. So quantum Hall doesn't quite fit into that picture, but it's still a symmetry-protected state in the sense that the symmetry that protects it is local gauge invariance, which is broken by coupling it to a superconductor, which is itself has broken local gauge invariance. And so that's why that makes it interesting, and it makes the effect very interesting when you couple it to the fractional cases, where I think quite a lot of work has been done here at Caltech on the interesting kind of generalizations of Majoranas that you can get by fractional quantum Hall coupled to superconductors, right? So one question is, why does it occur? Why would it occur in a lattice system? Well, in the Landau levels, of course, are the archetypal flat band, and the basic system is you have to have an ordering of energy levels where there's some bandwidth, which would be, in the Landau level case, the Landau level broadening, or the period, the magnitude of some one particle substrate inhomogeneity. Has to be small compared to the interaction energy, which has to be small compared to the gaps between the Landau levels, which are the gaps between the bands. And of course, that's what the people, I guess Neupert and Claudio Chamon, and people who actually took this original toy model here and found out by tuning you've got a bond here, this complex bond that hops across here. If it's purely imaginary hopping, it preserves the particle Hall symmetry of the two bands, but if I make it more general, then I destroy the particle Hall symmetry, and they found by tuning it appropriately, you could make the lower band shrink to become extremely narrow. And so just by taking this toy model and finding a parameter range which shrunk, which made one band very narrow compared to the other and compared to the gap, they found by numerical diagonalization of this thing that you would have states which, I guess through the entanglement spectrum, were later confirmed to be Laughlin-like. Okay? So the question that arises is, how do Laughlin states fit onto a lattice, or why should they fit onto a lattice? Because the Laughlin state, in its traditional explanation, it's got this holomorphic structure, which is supposedly something to do with the lowest Landau level, which in fact is an incorrect statement. And that seems to be nothing like the kind of structures you get for hopping around on a lattice. Even if there's a topological band structure, it's not described by holomorphic functions, which are to do with. So one question is, where do holomorphic functions come from in this thing? And as I say, Laughlin introduced it by saying, well, this is the lowest Landau level. And of course, it is true that if I take Galilean invariant Landau levels, they have the property that the wave function is a holomorphic function. But it turns out that's completely irrelevant to the issue. That's got absolutely nothing whatsoever to do with the holomorphic structure of the Laughlin state. So it's a kind of confusion that hides where it comes from. So the holomorphic structure of the Laughlin state comes from the noncommutative geometry of guiding centers, which is not there's also a noncommutative geometry of Landau orbit radius vectors, but these are separate things, and the fact that it's got nothing to do with Landau level structure directly is at least hopeful for the lattice, understanding how you can get the thing on the lattice. So the message I would like to be saying is that I believe that the quantum geometry here, and I'll show you there's a quantum geometry on the lattice, are the common things that allow Laughlin-like states to exist in one and the other. Okay. So this is a bit contrary to the wisdom of the conventional wisdom, and I would say that so we'll say that Laughlin has this underlying geometric properties which took a long time to be spotted, basically because they were sort of deeply hidden in this old interpretation of holomorphic structures coming from Landau levels. And so in fact, the Laughlin state continues to deliver in some sense. Every time people take a look at it, from time to time, some new insight seems to emerge. Composite bosons, composite fermions, now geometry. And of course, it's all the non-abelian things come out of generalizing ideas that come out of Laughlin state. And of course, the key thing that Laughlin state got right is it describes flux attachment, which is the basic physics of the fractional Hall effect. Flux attachment to form composite particles. Okay. So as I say, when Laughlin brought his state out, it was quite quick that this validity was confirmed, but in some sense, the question, we know it works, but the question of why the Laughlin state works has never really been answered. People have come up with, you wave your hands and say it's a clever state that keeps the particles apart. But those are kind of statements that don't allow you to say when a Laughlin state will be the ground state and when it won't, and etc. And so we actually need a more quantitative understanding, and I believe that should come from a geometric picture. So as I say, the Laughlin state, the misconceptions about it are, one misconception is it describes particles in the lowest Landau level, and in fact, when you look at it more closely, there's no specifics about which Landau level you're in, or even what the structure of that Landau level is. It's completely determined by the structure of the guiding centers, which are common to any system of Landau levels, whether or not they're elliptically shaped or circular shaped or other shapes that come out of Ashcroft and Mermin or whatever from the band structure. And secondly, Laughlin said, I've got a wave function, but actually once you project into a Landau level, you no longer have a Schrodinger representation anymore, because you've got the coordinates, spatial coordinates have been transformed into non-commuting coordinates, and you cannot have, Schrodinger doesn't work for non-commuting things. Schrodinger and Heisenberg are only equivalent for commuting coordinates, and they're equivalent, but once you remove locality from the picture, Schrodinger is not possible anymore, and Heisenberg is still perfectly fine. So it's really a Heisenberg state, not a Schrodinger wave function, although we always say wave function. And as I say, the shape, the circular shape it contains was initially identified with the Landau orbit shape. And of course, if you have a rotational symmetry, both the Landau orbits and the correlations will have the same shape. But if I break the rotational symmetry by tilting magnetic fields or something, there is no particular connection between the Landau orbit shape and the things. And the third thing was that when Laughlin brought his state out, it was remarkable because he said, here's a variational state, and there was no apparent continuous parameter to tune. There was the value of the exponent, but had to be an odd integer, so that wasn't tunable, just fix the pulling factor. And initially, some people thought, well, maybe all I have to do is find a better variational state and they'll win, right? But actually, Laughlin, as I say, Laughlin beat all these kind of slated determinant type ansatses, even though you could tune them how you wanted, because without any tunable parameter. But it actually does have a continuously tunable parameter, which was hidden for a long time. And as I say, for the 2D Landau level picture, we actually need because of this non-commutative geometry, the fuzziness of the states of the guiding centers, we need to actually go from the Schrodinger to a Heisenberg formulation to properly understand the state. And we'll see where the fuzziness happens in lattice systems when you project into bands. So the basic thing is you've got the order of things is you first do the Landau quantization, and then having done that, you project into a Landau level, and you have an effective interaction that depends on not just the bare Coulomb interaction, but also the form factors from the shape of the Landau orbits, which will smooth out the interior part, the part where the particles come together. So our basic problem has been reduced completely to this simple problem of interacting non-commuting guiding centers. And actually, just from that problem, you start to see that, you know, discussions of things like cone theorem, for example, which is a Galilean invariance theorem, have no place in the proper theory of the fractional Hall effect. They're all details of specific implementations, but the basic picture is to understand why this Hamiltonian sometimes gives rise to incompressible states with a quantum Hall effect. Sometimes it gives rise to Fermi liquid-like states of composite fermions, and other times it gives rise to spatially broken, symmetry broken states with stripe and bubble phases and things. Right? So Biockham's razor principle says that everything, this Hamiltonian of non-commuting coordinates is powerful enough to contain everything, and so any details which are not in here cannot be are not essential details to understanding, you know, why fractional Hall effects or other states form. And it turns out this is interestingly an ultra smooth. This potential is ultra smooth. Mathematically, it turns out to be, because you've got a potential which is a function of non-commuting coordinates, you've got some difficulties. You've got to be able to expand it to put meaning and then form symmetrized products and things to give meaning to this, to actually make it. It turns out that this is the condition for this to be meaningful is that this potential V of R, potential of a two-dimensional space, is actually entire in the extension from 2 real to 2 complex dimensions. So it's got and that's assured by the Landau orbit structure. The form factors guarantee this exponential, like Gaussian-like fall off, because the states are localized around these closed orbits, so that they actually give you exactly the right condition that this is a meaningful function of non-commuting coordinates. So it's very smooth, and you can see in this two-body Hamiltonian, the only two symmetries which are generic are translation and inversion. Rotational symmetry would be a special case if I wasn't of a particular shape of this potential, but there's no fundamental relation for rotational symmetry in this problem, but inversion is very fundamental, and it turns out inversion is the fundamental symmetry of the fractional quantum Hall effect, which has unbroken inversion symmetry. So where did it all come from? Again, it's this guiding centers. You've broken up, you've basically split up the electron coordinate into two parts. This is the coordinate, this is the Landau radius vector of the Landau orbit, and the difference of those is the guiding center. So you've written the commuting coordinates as a sum of two things which have equal and opposite non-commuting terms in it. So, and of course, once you quantize the Landau levels, you've thrown away the R bar degrees of freedom are frozen, then you're left with this non-commutative geometry. So where does holomorphic stuff come from? In fact, it's just a property of the Heisenberg algebra. So once you realize there's no connection to Landau orbits in the thing, and you shouldn't even think about what the Landau orbits are doing, you want to see what the fundamental representation of the guiding center algebra is. It's a Heisenberg algebra, and the fundamental representation is just the usual operators that we're kind of familiar from harmonic oscillators, right? So, but the thing is to convert the 2D coordinate into a creation operator which obeys a raising operator which obeys the standard commutation relations. You need a complex unit vector, and most of the time people have written down x plus iy for this unit vector, but there's no particular reason to do that. It's your choice. There's nothing in this problem so far that tells you which one you should do. It's a complete freedom of choice. You could have used anything that obeys this, and once you've got a complex unit vector, you have a metric. So basically the representations of the Heisenberg algebra are parameterized by a freely choosable determinant 1 Euclidean type metric. But it's your choice. So actually, and then holomorphic comes about that if any n-particle state has holomorphic states where once you've defined this complex structure, which is which defines the definition of something like Z, you have it defines a vacuum, and any many-particle state is a holomorphic function of creation operators acting on the vacuum. So holomorphic structure is purely a mathematical thing that comes out of this type of representation of the Heisenberg algebra. So when you do things like put this on a torus or whatever, you can also have a different Landau type representation where you diagonalize along lines, translations and things. But there you have a natural series-based representations. Here you have natural non-normalized and non-orthogonal kind of product type representations that are natural ones to make by specifying where the zeros of the holomorphic functions are. But so holomorphic there has got absolutely zero to do with Landau level, being in the lowest Landau level. And that's something that probably 90% or more of people repeat, say it's to do with the lowest Landau level, it's to do with the lowest Landau level. Absolutely false. Okay. So where can we find a non-commutative geometry on a lattice? Well, a topologically non-trivial band structure needs at least 2 orbitals in the unit cell. But if we actually project, but we want to have a description which references only the single topological flat band itself, which is like projecting into a single Landau level. So of course, once you project into a band, there's only one independent state, one orbital per unit cell. So that means that if I look at so if I actually project the local orbitals into the band and renormalize them so they have weight 1, then in that case I will find out, of course, that the anti-commutation relation, if these are fermions between the C daggers and the C's, is no longer 1 or 0. It's the overlap matrix between these renormalized states on each band. And this actually means that if I actually write down a Hamiltonian which is nominally purely on-site, like gauge invariant in these orbitals, so it only involves the number operator on these projected orbitals, very much like the fractional quantum Hall effect Hamiltonian has this form. There's no things. You just have in fact, then I will find that because there's a non-trivial overlap matrix between these things, this has non-trivial dynamics. The same way that there's no kinetic energy in the guiding center description of a projected Landau level, but the fact that particles move around, have a dynamics, comes completely from the non-commutative commutation relation between the guiding centers, or the non-orthogonal. If I make Gaussian coherent states at the nano level, which are the closest thing I can get to a localized particle, those are non-orthogonal, and that's why we get this thing, fuzziness. So the projected lattice is also, in some sense, a fuzzy lattice, and you can talk about a quantum fuzzy lattice because the geometry is totally encoded in the algebra of the operators. Because we'll find from this that first of all the complex structure Sij is a positive definite Hermitian matrix, a positive indefinite Hermitian matrix. It's got lots and lots of zero modes because the projected basis is over complete. But the complex part of it, the complex phases encode all the geometry, the non-trivial geometry of the Chern insulator band. And the spatial geometry, there's also a quantum distance, which is just 1 minus the absolute value of this overlap. So of course, if I have a classical system where Sij, a classical lattice where Sij is delta Ij, then the distance measure is a trivial distance measure. Your distance measure is 0 if you're the same site, and 1 if you're not the same site. Here I've got a non-trivial distance measure on the lattice built in. So this is the quantum geometry of the fuzzy lattice. And in fact, if you have a basis of of course, to get a basis of orthogonal states, you just have to diagonalize the overlap matrix. And of course, only the states which have non-zero eigenvalue, the non-kernel states, give you the basis of independent basis of orthonormal states. And in fact, if you do the same thing with the coherent state basis of within a Landau level, the overlap between two coherent states with a given choice of metric, which defines z, is of this form here, this Gaussian form. It's not z minus z prime squared. It's got this it's got z star and z prime here. That's the gauge part. But you diagonalize this thing, the integral equation for this, and of course you find out that the non-zero eigenstates are they're all degenerate, and they're all of the form of a holomorphic function times a Gaussian. So actually this is where you recover the holomorphic structure of the sort of wave function description of Landau levels. Okay, so anyway, so for the basic physics and energetics of fractional Hall involves flux attachment, and what I think is needed is a detailed physical understanding of this energetics, and then transform it in a way that removes reference to Landau level structure itself, and makes it more general, that it applies equally well to lattices and Landau levels, and I think the common theme will be the quantum geometry of the two systems. So I don't know if I've got much time left, but let me just go through a few things. Yeah, so when you have this potential, this smooth potential, of course, you can solve this as a two-body problem, and of course, when you solve it, you find you have a set of upside-down energy levels in this upside-down potential, and the highest ones are nearest the center, and of course, the gap between the top one, the close-in one, and the other ones is what favors flux attachment. If you can keep if you can keep any pair of particles from getting into the top state, that's what the Laughlin state does. You lower the interaction energy, and this basically gives rise to something which is very analogous to the picture one has of a quantum solid. We have a vacancy in the fluid surrounding a particle, and so we have these two things. We have the flux attachment, which can be thought of as a vacancy, and we have a particle in it. And this is very much like a unit cell in a solid. In fact, the second picture makes this thing. If we have a picture of a quantum solid, we can ask, when is a quantum solid stable? And one way to think about it is, if you remove a particle or remove all the contents of a unit cell, more generally, you'll be left with an attractive potential. And the question then is, if I put the other particles back, is this potential deep enough or strong enough to bind them, right? Of course, as you reduce the pressure in helium, the potential gets weaker because the thing is more floppy, and eventually it doesn't bind anymore. So in a quantum solid, the stability that drives it is whether is the binding of a particle to its own vacancy, which defines a position relative to the other particles. And of course, that's actually going to be the same thing in the fractional Hall effect. And the other thing that one wants to worry about is where things like dispersion relations come from in this guiding center thing. So it turns out that the dipole moment, when we go back to this picture here of the particle displaced in a solid, you have two types of excitation. You have the acoustic phonons, which can be viewed as the inversion symmetry preserving changes of shape of the unit cell. And then there's the optic phonons, which are the displacement of the particles to form dipole moments or currents relative to the inversion center of the unit cell. Well, the flux attachment has a similar property. The particles go in, and if the particle is displaced relative to the center, before the flux attachment occurred, there was no natural point to measure the displacement of a particle against. So the guiding centers actually, when you look at it more closely, because they involve subtracting p minus EA from the coordinate, they have a gauge ambiguity by adding a constant gauge to the term. But just as in a solid, once a unit cell forms, there's a natural place to measure displacements of the particles in that unit cell. Once the flux attachment forms, there's a natural place to measure the displacements of the particles relative to that, and that turns to the displacement of the guiding center into a physical object, the electric dipole moment of the object. And so because in a magnetic field there is this relation that the momentum is related, there's a term in the momentum, the D cross B term for Maxwell, ends up with the dipole moment times the magnetic flux density gives you a momentum. And so the relation between dipole moment and momentum says that the dispersion relation of this neutral object, which has formed the flux attached particle, is just its electrostatic energy as a function of dipole moment. Okay, so when one wants to look at dispersion relation of composite fermions and their Fermi surface, it's going to come from the electrostatic energy of deforming the composite particle away. So it's not one of the mysteries in quantum Hall was the Newtonian inertia. Was the electron mass happening in the early Chern-Simons plus Newtonian particle days, right? And the dispersion relation is totally this internal electrostatic thing. So I probably running out of time. So maybe I'll just show you a few things. So one thing is, what's the physical meaning of the metric that parameterizes the Laughlin state? And the Laughlin state differs totally from the filled Landau level. It looks very similar. The filled Landau level is a Slater determinant Zi minus Zj. Laughlin state is Zi minus Zj to the nth power. But the filled Landau level is a Slater determinant, an uncorrelated state with no correlation hole. And okay, if you take it on the plane, you vary the metric, you're going to vary the shape of the droplet. But if I put it in a box through periodic boundary conditions, nothing changes. The only thing that changes internally is the normalization constant. This is an unnormalized state. By changing the metric, basically by filling a different set of orbitals, just by changing the basis in which you fill up a closed shell to form a Slater determinant doesn't change anything except possibly the normalization constant. So on the other hand, the Laughlin state with different values as metric are completely different states. So because they have a correlation hole with a different shape, and as I say, the basic picture of the quantum Hall effect, I believe, should be, so the basic entity which is equivalent to the unit cell of the solid is the original composite boson picture of McDonald and Gervin. And as I say, the new features are that the whole, just like a unit cell has geometry, the flux attachment has a geometry too, and there's similar physics to the Hubbard model that once you've occupied your unit cell or your flux attachment, it costs you too much energy to put extra particles in it. So let me just skip on some of this and just see how this fits into the composite bosons and composite fermions, because both of them come out rather nicely from this analogy with solids. So the Laughlin state, the 1/3 Laughlin state, you've got 3 orbitals inside your flux attachment, and of course the best place to put the first particle is at the bottom. And there's some rearrangement, and in fact, by looking at the difference of the distribution compared to putting the extra particle in the lowest orbital rather than smearing it out uniformly, defines something called the spin of the composite bosons, which ends up coupling to the Gaussian curvature of any spatial variation of the metric. So you go to the 2/5 state, it's kind of similar, and you actually see the Jane sequence would come from essentially you fill up the orbitals in order of the Pauli principle, and so the levels inside the composite bosons can be thought of as Jane's fictitious Landau levels in this projected Landau level thing. So if you actually look more closely, then in fact the 2/5 particle, which is 2 particles bound to 5, if I have one of these objects swimming around in a background sea of 1/3, that's precisely the plus 1/3 charge quasi-particle of the Laughlin state, which is quite asymmetric, completely different from the quasi-hole, which is just an empty flux. But if you look at this system, you can see that just as charge transport occurs in a solid, if you now have a few unit cells which have excess electrons in them by doping it, of course, in the solid, the unit cells, if they're next to each other, they don't move. The difference between the solid and the liquid is that in the liquid, there's no, even if 2 composite bosons are adjacent at time t equals 0, they will not be later, while in the solid, unless a dislocation passes through, 2 neighboring unit cells remain neighboring. Right? But the charge transport occurs between the contents, the excess contents hopping around. So if you actually have 2/5 states here, the natural way that the charge hops around is by essentially a composite fermion, which is two fluxes and 1 electron, just being transferred from side to side. So you can actually see in this picture that with the composite bosons being the analogy of the unit cells, the composite fermions are the mobile charges that can hop between the unit cells. And you can start to make this picture look in some ways conceptually similar to solids, and you can start to ask what is the energy you gain by putting flux in a certain way. And of course the usual picture is that you have neutral bosons that move and they carry a dispersion that's related to the electric. The dispersion relation is the energy as a function of electric dipole moment. I'm probably out of time on this thing, but we did start a little bit late. But okay, so in fact, why the interesting thing is that just as in quantum Hall ferromagnets, the electron couple not just to the single gauge field, which is the magnetic flux density, but when you have a quantum Hall ferromagnet with a spatially varying spin order parameter, you also couple to the Berry curvature of that spin thing with the Pauli spin of the unit cell. So it's spin a half if 1 Landau level is filled. If two spin polarized Landau levels were filled, it would be spin 1, etc. Well, in this thing, you could also couple to spatial variations of the shape of this thing in a similar way. You couple to the Gaussian curvature. So there's a term that allows you to couple to this is the Wen-Z term, or part of it. There's a coupling to the Gaussian curvature of the guiding of the flux attachment shape. There's also, if the Landau orbit shape was varying spatially as what would happen as a surface acoustic wave went through, for example, you would actually couple to that too. There would be 2 terms. The so-called shift is a combination of the coupling to the guiding center and the coupling to the Landau orbits. But the interesting one is that the guiding center geometry can self-consistently adjust to compensate for spatial inhomogeneity. So if if you have regions of high potential, I can shift the charge away from that at the expense of some local deformation of the shape. And so from the edge of the sample, for example, you can squeeze the shape of the orbits when you have differential flow. And this is, again, this whole viscosity terms you get here. And nearer, and if you have near the quasi-holes or quasi-particles where there's excess charge, you should also get some adjustment that moves charge around. So there's quite a lot of richness in geometry in the Hall effect. And of course, the main thing is to understand, what to think of flux attachment in a very physical way and come up rather than as an abstract thing. And that, I believe, should be the key to understanding when and how to stabilize different kinds of states, both on the lattice and on here, on the Landau levels. Thank you. This picture for us. Okay.
Thank you for this. This very profound talk, and I actually have lots of questions as an experimentalist. But I'm going to allow just a couple of minutes, quick questions from the theorists. Yes, Jason, please.
It's just it's a comment rather than a question, but there's a beautiful experiment that I actually just learned about yesterday by Andrea Young, where they actually do see, I think for the first time, fractional insulators.
Yeah, I think I saw that came out, right? Yeah, it was. This is in a Hofstadter type situation, right? Yeah.
So some of these ideas actually.
Yeah.
We now have a laboratory technology.
Yeah. So I think there's, flat bands and things are going to be a big part of our future, because really interesting things can happen in flat bands.
Any other burning questions? Otherwise, we will also have time for discussion later. Yes.
So you explained that everything is in geometrical lattice. So as presumably Laughlin state 1/3 and 2/5 hierarchy states, all these things is
Yeah.
in the same class.
Yeah.
Now what about the 5/2 state?
Yeah.
That's supposed to be a lot more complicated than
No?
get away from.
Okay. From this picture, I don't yet see how you predict when it's non-abelian or not, because it's really a question of how the thing can break up, I think. But the 5/2 state is well, first of all, there's a selection rule that you have this feature. This is the modern form of the odd denominator rule. So 5/2 is really 10/4, okay? Because 5/2 would be 5/2 is a fermion. 10/4 is a boson. And so the flux and the charge are independently meaningful things. The filling factor is just a ratio of the two. So from the fact it's 4, for example, it's 10/4, the fact that the 4 fluxes with, in fact, you can probably throw away the lowest Landau level. So it's 2 particles in 4 fluxes. That tells you that the basic non-abelian, the basic charge is 1/4, right? And so I would draw the same. I would just draw a picture of the 4 fluxes, and then the lowest, the 2 at the bottom are occupied. The next 2 are empty. The particle hole transformation on this will actually have the 2 at the bottom empty and the top 2 filled. And if it exists, which we're kind of dubious about, the so-called T-Pfaffian, the thing would actually have the second and third one filled, and the top and the bottom one empty. But so the details of different kind of quantum Hall states, just like in a solid, the different ways you can arrange the components inside the unit cell give you different energies and different structures and what. So just in the quantum Hall state, the details of how the more than, if there's more than one charge in this flux attachment thing, then you've got the same sort of approaching the kind of richness you have in solids, that you have to find out which is the lowest. So actually we're kind of pursuing the thing of seeing if one can do some mean field picture that actually starts with the hole in the background and sees if you can get some quantitative estimates of different kinds of binding energies or not. Be kind of interesting to see if it works. Yeah.
Okay, in the interest of time, let's thank Professor Haldane again.